We're very happy to have Michael Hutchings talking today about examples related to Viterbo's conjectures.
All right, thank you very much for the invitation. I just got this new iPad, so let's see if I can use this thing. So let me review a couple of basic things. So these have been covered in some previous talks here, but in case anybody wasn't there. Everything I'm talking about originates from questions about symplectic embeddings. And in particular, I'm just going to talk about domains in R2M with the standard symplectic form, although you can also talk about other kinds of symplectic manifolds if you want. And some basic examples that people like to play with. There's the ball B of R, which is the ball such that a two-dimensional slice through the center has area R. There's the cylinder Z of R, so that's the symplectic product of a two-dimensional disk of area R with R to the 2n minus 2. There's also the polydisk P of A1 through AN, which is the symplectic product of two-dimensional disks of area A1 through AN. And then there's the ellipsoid E of A1 through AN, which is the set of points such that the sum of pi times absolute value of zi squared over AI is less than or equal to 1. So if you, in particular, if you set all the numbers A1 through AN equal to R, you just get the ball B of R. So people ask various questions about when you can symplectically embed one of these things into another, and other examples too. So just to recall, if you have two different domains, X and X prime, symplectic embedding from to X prime, and I can make corrections on my notes. This is fun. I just got this new iPad. So it's a smooth embedding which respects the symplectic form. And in particular, because the symplectic form determines the volume, if there exists a symplectic embedding from X to X prime, then the volume of X must be less than or equal to the volume of X prime. But the very famous non-squeezing theorem of Gromov says that this volume condition is far from sufficient for the existence of a symplectic embedding. So that theorem says that if there exists a symplectic embedding of the ball into the cylinder, then the size of the ball has to be less than or equal to the size of the cylinder. So you can't take a big ball and squeeze it into a skinny cylinder, even though there would be no problem doing with the volume observing embedding because you can just shrink in one direction and fetch in another. There are many other theorems on this subject. I'm just going to mention one that I like, which is related to some things I'll say later. And there's many more things after that. So this is a theorem of Dusa-McDuff. She proved that if you look at four-dimensional symplectic embeddings, then four-dimensional ellipsoids, then there is an embedding of an open ellipsoid, E of A1, A2 into E of B1, B2, if only if a certain numerical criterion holds. The criterion, so you have a sequence of numbers, N of A1, A2. And this sequence of numbers is the set of all non-negative integer linear combinations of A1 and A2. And you write them in increasing order with repetitions. And the symplectic embedding of ellipsoids exists if and only if this sequence for the first ellipsoid is less than or equal to the sequence for the second ellipsoid, term by term. So in theory, that's a combinatorial criterion for when the embedding exists. Although, if you're given specific numbers A1, A2, B1, B2, if you want to check this criterion, then it says something about every K. So it's a little bit complicated to check, and this leads to some beautiful combinatorics. So in Deuce's talk, she talked about a more general version of this, where instead of embedding an ellipsoid into an ellipsoid, you embed it into a Hutchings surface, and they can do incredibly detailed calculations of when these embeddings exist or not. In dimensions higher than 4, we don't have any theorem like this. There's some partial results, but it's much more open. Now, to study these kinds of questions systematically, there's a notion of symplectic capacities. There are different definitions of this in the literature. So the definition I'm going to use is a symplectic capacity is a function C. It inputs some domain X and R2N, and maybe not all of them. Maybe you have to assume something about X. And it outputs a real number, anything from 0 to plus infinity. And it has to satisfy two properties. First of all, monotonicity says that it gives an obstruction to the existence of symplectic embeddings. So if there's a embedding of X into X prime, then the capacity of X is less than or equal to the capacity of X prime. And it also should scale like a two-dimensional area. So if you take a domain X and just scale it by R, then you use capacity. And we further say that a symplectic capacity C is normalized if it's at least defined for all compact convex domains, and it satisfies the property that the capacity of a ball of size R is equal to the capacity of a cylinder of size R is equal to R. So there are lots of symplectic capacities, some are normalized, some are not. And here's some examples. So the first example of a normalized symplectic capacity is the Gromov width. And this is defined to be the size of the largest ball, or a little more correctly, it's the supremum of the size of a symplectic ball that can be symplectically embedded into X. So this is obviously monotone, because if I can embed a ball into X, and if I can embed X into X prime, then I can embed a ball into X prime by composing. And it's also conformal because of my convention for what B of R is. And it satisfies the property for the ball because you can't embed a bigger ball into a smaller ball because of the volume. And the only non-trivial property to check is the capacity of a cylinder. And this is what the Gromov non-squeezing theorem says. It says that the Gromov width of the cylinder of size R is equal to R. So the Gromov non-squeezing theorem you can think of as being equivalent to saying that a normalized symplectic capacity exists. There's a variant of this called a cylindrical capacity. I actually like to think of this as uncertainty. Hold on, I've lost my pencil. So it's the infimum of the size of a cylinder that you can embed X into. It's equivalent to saying you can apply some morph to X, some other domain in R2N, and you want to minimize the area of the projection to a two-dimensional symplectic subspace. So it's sort of like a classical version of the uncertainty principle in quantum mechanics. And you can similarly check that this is also a normalized symplectic capacity. So these are easy to define. In general, they're difficult to compute. Another very interesting example is called the Ekelund-Hofert-Sander capacity. So there were several different definitions which were by subsets of these authors, which were proved to be equal. So if you assume that your domain is convex and has smooth boundary, then it has a ray vector field on the boundary. The same is true more generally for any star-shaped domain. And you can say, what is the minimum period of a Rabe orbit on the boundary? So that's a number. We know this is one of the first cases of the Weinstein conjecture to be proved that such a Rabe orbit exists. So you can say, what's the minimum action? It's not at all obvious that this, as defined, is a symplectic capacity, because it's not clear that it's monotone. If I can symplectically embed one convex domain into another, why should the minimum action of a Rabe orbit of one of them be related to the minimum action of a Rabe orbit for the other? So that is known to be true by comparing this with some other definitions of the capacity. And it's only true for convex domains. If I could make the same definition for star-shaped domains, but it wouldn't be a capacity anymore. So those are some normalized symplectic capacities. There's some interesting non-normalized symplectic capacities too. Sorry, this slide has a lot of junk on it. Anyway, there's there's a whole sequence of capacities. So I studied these in a paper with Sean Goots, although these numbers have been studied previously by other authors. So we call this kth equivariant capacity, although we denote it by CKCH because secretly we're thinking of this as being defined using linearized contact homology. But for the purpose of writing rigorous proofs, it's a little better to use the positive S1 equivariant symplectic homology. So informally, so there's one of these for every positive integer k, and informally, this is the minimum symplectic action you need to represent the case generator of contact homology. So this is useful for some symplectic embedding problems, but in general, it's not normalized. So the capacity of a ball size r, well, the k nth capacity is equal to k times r. So you basically, you repeat the number r n times. So the sequence of capacities goes r, 2r, 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 and so on. You repeat each multiple of r n times. The capacity of the cylinder, the kth capacity is just k times r. If n is bigger than 1 and k is bigger than 1, then these numbers are different. There's another sequence of symplectic capacities defined using embedded contact homology. These are called ECH capacities. Again, you can compute the capacities of a ball and a cylinder, and they're different for k bigger than 1. And you can't make it normalized by multiplying by some constant because the capacity of a ball is less than the capacity of a cylinder. There are also capacities you can define geometrically. So a very interesting one, this is just an example of one of my favorites. It's introduced in a paper by Symplectic and Monke, and you look at Lagrangian tori in X. For a Lagrangian torus, you define its size to be the infimum of the area of a symplectic disk with boundary on the Lagrangian torus. And I try to make that size as big as possible. So the Lagrangian capacity of X is the supremum of the size of a Lagrangian torus in X. So this is not a normalized capacity, but Symplectic and Monke computed it for a ball. They find the capacity of a ball of size r is r over n, and this capacity of the cylinder of size r is equal to r. And there are many other examples of symplectic capacities, so I'm just telling you a few. This is a digression from what I'm supposed to be talking about, but I think it's cool. So these two sequences of symplectic capacities have some asymptotic properties. So the ECH capacities, if you take the limit of ck squared over k you recover the volume of the domain. So the general version of this is in a paper with Dan Christopher Gardner and Vinicius Ramos. And this has all sorts of applications. I think we heard some talks about this. I don't remember if it was this seminar or a different one, but there are lots of applications. For the equivariant capacities, there's at least some evidence that the asymptotics of them is related to Lagrange capacity. So you look at the limit of Ck over K, and at least in some cases, these are known to be equal. Seeley-Bach and Monka proved this for a ball, and there's some other cases that are known. There's some work in progress on this going on, but it's not my announcement to make, so I'm not going to say anything. But there does appear to be some relation between these. Now let's turn to Viterbo's conjecture. So this is the first conjecture I'm going to say here. This is not actually what Viterbo conjectured in his paper. So if it turns out to be wrong, please don't hold him responsible for this statement. I'm told that this was folklore going around in the 1990s, but I was not working on this subject at that time. I am actually old enough that I was doing math then, but I was not working on this. So I don't know who said this, who believes it. Anyway, it's related to Viterbo's conjecture. So I'm going to call it the strong Viterbo conjecture. And the statement is that if you have a compact convex domain in R2n, then all normalized symplectic capacities are the same. So just to put that in context, it follows immediately from the definitions that any symplectic capacity, any normalized symplectic capacity, is in between the Gromov width and the cylinder capacity. So the Gromov width is less than or equal to every other normalized symplectic capacity, and the cylinder capacity is greater than or equal to every other normalized symplectic capacity. So an equivalent statement is just that if X is a compact convex domain, then the Gromov width and the cylinder capacity are the same. No, it's a statement. Is it true? I don't know. This is what actually appears in Viterbo's paper. So the conjecture is that if I have a compact convex domain, and if C is a normalized symplectic capacity, then it satisfies a kind of isoparametric inequality. So it says that the capacity of X has an upper bound depending on the volume. So C to the n over n factorial is less than or equal to the volume. And moreover, equality holds if and only if the interior of X is symplectomorphic to an open ball. So it says that a normalized symplectic capacity is maximized. If you fix the volume of the domain, it's maximized for the ball. And for anything else where the interior is not symplectomorphic to a ball, the capacity is small. So the first part of this conjecture, the inequality, it follows from the stronger conjecture on the previous page, because this inequality must hold for the Gromov width. And the reason why is because the volume of a ball of size r is given by this formula. It's r to the n over n factorial. And because of the volume property, the Gromov width of any domain has to be less than or equal to r, such that the ball of size r has the volume can't embed into X of ball, which has volume bigger than the volume of X. So that implies this inequality here. But then the strong version of Viterbo's conjecture says that all normalized symplectic capacities are equal. So that would mean that in this inequality, you could replace the Gromov width by any other normalized symplectic capacity, and then you would get this inequality. Okay, and then there's a weaker version of this conjecture, which is actually quite interesting. So to state the weaker conjecture, let's define the systolic ratio of a star-shaped domain. I better assume the boundary is smooth. As follows. So you let A min of X denote the minimum symplectic action or period of a ray orbit on the boundary. And then we define the systolic ratio to be the minimum action to the nth power divided by n factorial times the volume. So the weak version of the conjecture is that if I have a compact convex domain with smooth boundary, then its systolic ratio is less than or equal to 1. So this is a special case of the previous conjecture, because remember that on convex domains, the minimum action is a normalized, well, I guess I didn't tell you that it's normalized, but it is known to be a normalized symplectic capacity, which is this Ecklenhofer-Zehner capacity. So if Viterbo's conjecture is true, then this Ecklenhofer-Zehner capacity has to satisfy this isoparametric inequality, and that isoparametric inequality is just that the systolic ratio is less than or equal to 1. And this is sharp in the case of a ball. So in the case of a ball of size r, in this case, the minimum action of a symplectic ray orbit is just equal to r. And the volume is r to the n over n factorial. So the systolic ratio is 1. So this is interesting from dynamics point of view. It says that if I have a convex domain, and here convexity is really a very important part of the hypothesis. But if I have a convex domain, then it has, not only does it have a ray orbit, but it has a ray orbit whose period is short with respect to the volume. And this conjecture has some interest outside of symplectic geometry, because it was proved to imply the Mahler conjecture in convex geometry. And this implication was proved by Arstein, Avedon, and Karasev and Ostrover. I think I got that right. So this is a quite interesting conjecture. So I don't know how to prove any of these conjectures, but I'd like to tell you some of what's known, or maybe prove some examples and bring up some interesting facts. Are there any questions about what these conjectures say before I start doing that? Okay. There was this funny cartoon about like what it's like to teach a Zoom class. So they had an elementary school class, and it shows so there's a panel of all the students, and they're all excited. Like, let me show you my cat. Look, I folded this piece of paper in half, and blah blah blah. And then there's a Zoom high school class, and you see a panel of just a bunch of black squares. Okay, anyway, please interrupt me if you want to ask something. Okay, so what can we prove? Well, one kind of, somebody have a question?
No, I'm just waving.
Oh, okay, hi, good to see you. But thank you for not being a black screen. You can be a black screen again. Okay, so one kind of partial result you can prove is you can say, well, let me write down all the normalized symplectic capacities I know and try to prove that some of them are equal to each other. So at least that's better than nothing. So if you combine results of Irié and Abendandolo and Kong, then they prove that if you have a compact convex domain, then the Ekelin-Hofer-Zehnder capacity, which recall is the minimum period of a Rabe orbit, is equal to the first capacity coming from contact homology. So that's kind of cool in my opinion. It shows that contact homology actually sees the minimum action of a Rabe orbit. And you can compare more normalized symplectic capacities with each other. I don't want to try to list all of the known normalized symplectic capacities, but I'll just remark in general, it's very hard to compute the Gromov width or the cylinder capacity. So these are easy to define, but they're sort of like out there in the sky somewhere, and we don't know how to compute them. Well, a lot of the other capacities defined using some kind of contact homology or Floer homology are actually computable, at least for some examples, and you can try to prove that they're equal to each other. But it's very hard to actually compare them to the Gromov width or cylinder capacities. In the four-dimensional case, if you have a convex domain or even just a dynamically convex domain, I'll review what that means a little later, then the capacity from contact homology is less than or equal to the capacity from ECH, but I don't know if that's an equality or not. You can also try to prove the conjecture in some special cases or for some special examples. So here's a nice one, which we learned about from Bruno Strover. So the strongest version of the conjecture is actually true for any S1 invariant convex domain. So it's really important that it's both convex and S1 invariant. And if that's true, then the Gromov width equals the cylinder capacity. So since every talk should at least prove something, let's prove this.
Michael, we lost your sound.
Maybe it's a harder proof at 6:45 a.m. than Michael realized.
Michael?
Michael, we can't hear you.
Michael's been muted.
I got muted somehow. Wait, what happened?
It's good now.
You were going to prove something for us, but then you were muted.
He's muted again.
You're muted again, sorry.
Oh, it's because Michael has his iPad on Zoom and his computer on Zoom, and so I think he's only trying to talk at one thing, but maybe...
Yeah, so I think the thing that's meant to be not muted is not working, and so you should unmute the one that's normally muted.
So my iPad is having difficulties, so I apologize.
So it happened exactly when you started the proof. So That's a strategic moment.
Looks like my iPad is still connected. Right, excuse me for 1 minute.
The screen off. The screen is off.
All right, I think my iPad is back. And now let me share again. Oh, you need to make me a co-host again.
Oh, sorry. All right.
I'm going to share the screen. Okay. All right. Sorry about that. I don't know what happened. Teaching has gotten very complicated these days. It used to be all I had to do. It was very important to make sure I have my own piece of chalk before going to the classroom because they were often out of chalk. Now I have to make sure the Apple Pencil is charged and all these things are connected. Yeah, okay, anyhow, apologize for that little technical delay. So anyway, we basically look at the largest ball that we can put in here. So by definition, the Gromov width is bigger than or equal to the symplectic size of that ball, which the way I've written things is now pi r squared. So to complete the proof, I just have to show that the cylinder capacity is less than or equal to that. Now, I use convexity to say that X is contained in the half space. That's determined by the tangent plane to the boundary of X at this point Z. So Z is, this is a very bad picture, but Z is over here somewhere, and there's a tangent plane, and the whole domain has to be on one side of that tangent plane. But then by the S1 symmetry, it's contained in a bunch of other half spaces as well. So it's not only contained in the half space where Z dot 1 plus R, but also where Z dot e to the I theta 0 is less than or equal to R. So it's contained in all those half spaces, and the intersection of all those half spaces is a cylinder, the same size as the ball. So this is a very not to scale picture. But anyway, that's better. I can cheat. So you find a ball, and your domain. If we do this right, so the purple thing is supposed to be convex. So you find that the domain is literally sandwiched between a ball and a cylinder of the same size. In general, you can't hope for that to be true, but in this case, it works. So that's nice. Here's another thing we can say. This is not a proof of the weak Viterbo conjecture. It's a proof of something. So suppose that we have a compact convex domain, strictly convex with smooth boundary, which maximizes the systolic ratio. Then the systolic ratio is equal to 1. So this is proved in a paper by Abundandel, Bernievich, and Solomon, and there's a similar argument in an earlier paper by Weinstein. So how does this work? Well, so every point on the boundary has to be on some Rabe orbit of minimal period, because if it weren't, then I could cut costs and shave a little volume off my domain at that point, and it wouldn't change what the smallest Rabe orbit is, but it would decrease the volume. and so it would increase the systolic ratio, which would be a contradiction. So now every point is on a Rabe orbit, and that means that the boundary of X, let's fix this little typo here. The boundary of X is a fiber bundle whose fiber are the Rabe orbits. Because the bound of X is, if you morph to a sphere, this fiber bundle has to be the Hopf vibration by a little topology. And then you can calculate its volume using the symplectic form and the Gauss-Bonnet theorem, and you find that the systolic ratio equals 1. That's very nice, although it does not actually prove the Viterbo conjecture because we have no idea whether such a maximizer of the systolic ratio with these properties exists or not. You notice also that in the middle of the proof, I never used convexity. So the same argument shows that if I have a local maximizer, which is star-shaped, then the systolic ratio is 1. And there are famous problems in geometry where there's a proposition like this, and they're local maximizers, but they're not global maximizers, and no global maximizer exists. But anyway, this is just despite those flaws, this is maybe a little motivation for why the weak Viterbo conjecture might be plausible. Philosophically, you can say, what is the role of convexity in this conjecture? And that's a mysterious question because being convex is not invariant under symplectomorphisms. So if the statement is true for everything convex and it's also true for everything symplectomorphic to a convex domain, which is a lot more domains, it's not clear exactly what assumption you would want to make. But it's certainly not true for all star-shaped domains because you can find star-shaped domains with arbitrarily large systolic ratio. One thing we do know is that for convex domains, the minimum action for Rabe orbit is C0 continuous because it's a capacity. So if I take a convex domain and deform it a little bit, you could have bifurcations where a pair of Rabe orbits could be created out of nothing. But that can never happen with a pair of Rabe orbits at a smaller action than what you've already got. And that's a very non-trivial fact. I think maybe one should be able to get some mileage out of that somehow. Hofer, Wazowski, Sander proved that if you have a convex domain with strictly convex boundary, then it's dynamically convex. And this is now a symplectically invariant condition. And it says that every Rabe orbit has Conley-Sander index at least n+1, which is a measure of a vector field rotates in the neighborhood of the orbit. So you could say, okay, good, we have a symplectic reformulation of the conjecture. Let's prove Viterbo's conjectures for every dynamically convex domain. But unfortunately, it doesn't work because ABHS found examples in R4 which are dynamically convex, but they have systolic ratio close to 2. So these are probably not symplectomorphic to convex domains, or if they are, they're counterexamples of the conjecture. You could still conjecture that every dynamically convex star-shaped domain in R4 has systolic ratio less than 2. I think that's probably true. And I want to tell you about some examples. So a way to make lots of examples of domains in Rn is toric domains. So you start with a domain omega in Rn. This is really a moment map image of your domain in R2n. And you define X omega to be the set of all Z in Cn such that the absolute value squared of each coordinate multiplied by pi is an element of omega. So for example, if you start with a triangle in 4 dimensions of side length A and B, then you get an ellipse CAB. And if you start with the rectangle, you get a polydisk. And there's some particular classes of toric domains that I want to talk about. And instead of writing down the definitions, I'll just draw pictures to give you the idea of what these are. So a convex toric domain looks like this. So omega itself is convex and it's not allowed to dip down. So another way to say it is if you take omega and take all its reflections across the axes, it's still convex. It's a slightly bad choice of terminology because a convex toric domain is not the same thing as a toric domain that's convex. I apologize for that. So every convex toric domain is in fact convex. However, there are also some toric domains which are convex, which are not convex toric domains. My apologies. My paper with Jean-Good and Vinicius Ramos explains this in detail if you want to see what's actually going on. A concave toric domain looks like this. So it's where the positive quadrant minus omega is convex. A monotone toric domain is one where omega is below the graph of some function, which is monotone decreasing. And a weakly convex toric domain is one like this, where omega is convex, but it's allowed to sort of bend over. So it's no longer, the boundary curve is no longer graphical. And then just to state some theorems. So the definition of monotone toric domains also makes sense in R2n. Basically, I want that the normal vectors to the boundary of omega away from the coordinate planes have all components positive. In the three-dimensional case, you can check monotone toric domains are the same as toric domains that are dynamically convex. So in the world of toric domains, dynamically convex is the same as monotone, up to some putting in the word strictly here or there. So that's a motivation for why those are interesting examples. And a theorem was shown in Vinicius is that if you have a monotone toric domain in R4, then the conclusion of the strong Viterbo conjecture holds. The Gromov width equals the cylinder capacity. So all normalized symplectic capacities agree. This is not really an example of the strong Viterbo conjecture. I had this slightly awkward title, like examples related to Viterbo conjecture, example around the Viterbo conjecture. And the reason for that is most monotone toric domains are not actually convex. So the Viterbo's conjectures don't apply to these domains. They're more general. So it's sort of saying, okay, let's look at some more general domains that aren't necessarily convex. Do the conclusions of these conjectures hold or not? At least for these monotone toric domains, the answer is yes. So let me indicate roughly what's involved in the proof. So we're going to take the largest ball that is a subset of the domain. So here it is. So that's the simplest thing you could imagine. So certainly the Gromov width is greater than or equal to the size of that ball. And then to complete the proof, we're going to prove the reverse inequality. We're going to show that this R is actually equal to the cylinder capacity. And for that purpose, there's another typo here. I need to prove that it's enough for me to show that the interior of my domain X omega embeds into a cylinder of size R. And for this last statement, there might be some direct construction of an embedding, but I don't know that. So we're going to use some very heavy machinery, which might be heavier than necessary. That's the theorem of Dan Christopher Gardner. This is really powerful. It says that if X is a concave toric domain and X prime is a weakly convex toric domain in R4, then there exists a symplectic embedding if the interior of X prime, if and only if all ECH capacities of X are less than or equal to the ECH capacities of X prime. So this condition on the ECH capacities is necessary for a symplectic embedding to exist because ECH capacities are monotone. So the non-trivial fact is to say that if I know this inequality and the ECH capacities, then a symplectic embedding actually exists. The construction is extremely indirect. But it's useful because there are known combinatorial formulas for computing these capacities. So you can actually apply this formula to examples, which I'll show you in a minute. I remark that this generalizes the theorem of Dusa-McDuff that I mentioned. So her theorem says that an ellipsoid embeds into an ellipsoid if and only if these numbers nk of one ellipsoid are less than or equal to the numbers for the other. These numbers in nk are actually just the ECH capacities. And an ellipsoid is both a concave domain and convex domain. So if you take X and X prime to be ellipsoids, then this theorem recovers Dusa-McDuff's theorems. So you could also look at embedding a convex toric domain into a concave toric domain, or a convex into convex, or concave into concave. In those cases, the ECH capacities do not always give a sharp symplectic embedding obstruction. But in this case, they do. So I'll use that fact to complete the proof of the theorem. So if I have my monotone toric domain, let's draw it in purple. So here R is the size of the largest ball that's a subset of the monotoric domain. Well, the monotone toric domain itself is contained in some larger, or the omega is contained in some larger omega, which is given by this polygon. So it's just a quadrilateral, concave quadrilateral. So I just have to prove that this whole thing, if I take this concave quadrilateral, then this X omega embeds into a cylinder of size R. And that's now more or less an example where Dehaen's theorem applies. So we actually prove is that this X omega embeds into a polydisk. The polydisk, the moment map image is a rectangle. So this thing is a convex toric domain. And this is a concave toric domain. So we just have to prove that the ECH capacities of X omega are less than or equal to the ECH capacities of the polydisk. And there's a fun proof of that using the formulas for these capacities, but I don't think I have time to explain that right now. So here's a Venn diagram to show what we know about the status of these conjectures in 4 dimensions. So really, the conjectures, as stated, are only applicable to convex domains, which are inside the circle. And I know that it's true for convex domains that are toric domains because they're S1 invariant. So I guess I could make a bigger, I can make another circle. I'm not sure where this is going to go. But anyway, it's known for convex domains that are S1 invariant. And it's known for toric domains that are dynamically convex. So that covers, didn't want to do that. That covers these 2 check marks here. So that's what we just proved. It's not known for general, it's known to be false. All the conjectures are false for general dynamically convex domains by these counterexamples of ABHS that I mentioned. If you look at toric domains, which are not dynamically convex, it's been known for a long time that there are counterexamples. And I'll show you some new ones that we can see explicitly. In higher dimensions, we do not know that the strong version of the conjecture holds for monotone toric domain, but we can at least prove that the Gromov width is equal to the first capacity coming from contact homology. And it's a similar proof. So you just take the largest ball, which is in the domain, and you prove that that's optimal. Let's look at some more fun examples. So what happens if you throw monotonicity out the window? Look at more general toric domains. So in the paper with Gut and Ramos, we looked at a domain like this. So it's bounded by a 5-gon. It's weakly convex. Sorry, yes, it's weakly convex, but it's not convex or monotone. So we could say, do the conjectures still hold for this domain? And it depends on a parameter A going from 0 to 1/2. So if A equals 0, this is a ball, and then we know that everything's true. And then as we increase A, we're chopping off corners from both sides of this triangle and shrinking it. So at what point do the conjectures stop working? So it's kind of fun that we can actually compute everything for these examples. So the proposition is that the Gromov width is the minimum of 1 minus A and 2 minus 4A. And while the cylindrical capacity is just 1 minus A. So if A is bigger than 1/3, then this minimum becomes 2 minus 4A. So for A from 0 to 1/3, the Gromov width and the cylinder capacity are the same. Then for A bigger than 1/3, the Gromov width suddenly starts decreasing faster than the cylinder capacity. And to prove this, well, we showed the Gromov width is seen in this case by the first DCH capacity. Although in this case, it's no longer true that you just take the biggest ball that's a subset and then that's optimal. So we can find the ball embeddings, but they're more non-trivial. And then to prove that the cylinder capacity is 1 minus A, well, this domain is certainly contained in the cylinder. See if 1 minus A, I can just draw it right here. This point is 1 minus A. So this whole purple region is the cylinder size 1 minus A. So it's a subset of the cylinder size 1 minus A. But why can we not symplectically embed it into a smaller cylinder? ECH capacities don't help. This is an example where Dan's theorem doesn't apply. So I wrote a paper called Beyond ECH Capacities, which looks a little more carefully at the holomorphic curves that are involved in these obstructions. And those methods work here to prove what we want, that the cylinder capacity is 1 minus A. So in this case, it's actually very simple. You show that if this domain embeds into a cylinder, then a certain holomorphic cylinder has to exist, where the action of the positive end of the cylinder is 1 minus A, or is the size of the cylinder, and the action of the negative end of the cylinder is 1 minus A. I just want to mention that if you're interested in feature conjecture, so finding the shortest Rabe orbit, then there are formulas for convex polytopes. So you have to be a little careful because the boundary of a convex polytope is not smooth, and it doesn't, strictly speaking, have a Rabe vector field, this singular part. But the definition of the Ecklenhofer-Zehnder capacity extends by continuity to all compact convex domains. So it still makes sense to talk about the systolic ratio of a convex polytope. You just define it to be CEHC to the n divided by n factorial times the volume. So the weak Viterbo conjecture is equivalent to the statement that for every convex polytope, the systolic ratio is equal. And Pazit, Haim, Kislev has a formula for this. It's a very complicated min-max kind of formula. But if you can process that formula, then boom, it tells you CEHC of any convex polytope in R2n. And in joint work with Julian Chides, we looked at the 4-dimensional case, and we did something a little more complicated, but it finds not only the shortest rate orbit, but it finds essentially all the rate orbits and also their Conley-Tanger indices. So we find a correspondence between rate orbits on some smoothing of the polytope, along with their actions in Conley-Tanger indices. We find a correspondence between those smooth rate orbits and some combinatorial data. So there's a combinatorial version of rate dynamics, and we have combinatorial Conley-Tanger index. So if you want to test some conjecture, then we can sort of compute these rate orbits for a polytope, and then we tested by computer to try to see if the weak Viterbo conjecture is true, which maybe that's sort of the hardest thing to find a counterexample to, because it's the weakest version of the conjecture. In any case, we didn't find any counterexample. However, we did find some interesting examples where the systolic ratio equals 1. So one nice example, which you can remember, is the 24 cell. So this is one of the 6 regular polytopes in 4 dimensions. And if you write it in this form, then it has systolic ratio equal to 1. So there are 8 vertices, so the form minus 1, 0, 0, etc. And then there are 16 vertices, plus or minus a half, dot, dot, dot. So for a total of 24 vertices. There are also 24 3 faces, which are octahedra. So you can check by hand that this thing is systolic ratio 1. By computer, we found an example with 6 vertices instead of 24 that has systolic ratio 1, so that was very non-obvious. And Viterbo's original conjecture would tell us that the interiors of these polytopes should be symplectomorphic to open walls, but I don't know if that's true. And I don't have any formula in general to compute Gromov width or cylinder capacity. Anyway, so that's a little introduction to some of the conjectures that I lose sleep over. That's the end of my talk. Thank you very much.
Right, thank you very much, Michael. Right, thank you very much, Michael. Thanks a lot. Thanks a lot. Of course, if there are any questions,
May I ask a question?
Of course.
Please.
May I ask a question?
Of course.
Michael, I was wondering if you have some ideas about how to approach the convex domain is symplectomorphic to a toric domain.
Do you think that's likely to be true? So that would be amazing if that were true. My Venn diagram here, I was thinking of the toric domains really being some sort of infinitesimally small sliver of the whole picture. So yes, if every convex domain were symplectomorphic to a toric one, then of course that would apply everything we want. That would be great. So the question would be: is there some kind of symplectic invariant that would allow you to prove that something is not toric?
Exactly. That's the. Exactly. That's the.
So I have one idea. So there's something called the Ruel invariant. And for a toric domain, for convex toric domain anyway, this Ruel invariant is just A plus B. You can compute it. So it might be that I have to think what the right statement is, but it might be that if you have some domain where the Ruel invariant is either too big or too small with respect to something else, then it can't be toric. We also have all sorts of formulas for capacities of toric domains, and you could look at their asymptotic properties, and maybe if you look at that carefully enough, you could see that something's not toric.
Okay. Thank you.
Sorry, Mike. A plus B is an invariant quad. Mike. A plus B is an invariant quad.
So the Ruel invariant is defined for any star-shaped domain in 4 dimensions.
Toric.
It doesn't have to be toric. So the Ruel invariant, this is defined for star-shaped domains. So it's a measure. Well, I can tell you what it is. So the Ruel invariant of X is, let's say in the 4-dimensional case. So it's the integral over the boundary of X of some number rho, or some function rho with respect to the contact volume. And what this rho is, this is a asymptotic rotation rate. So you start at a point, you take a very long rate trajectory, and you see how much the rate flow is rotating around the very long rate trajectory. And then
it's the Conley-Zender index around the. So it's the Conley-Zender index around the.
Yeah, it's basically the Conley-Zender index, maybe divided by 2 or something.
We have a terrible echo. I don't know what. We have a terrible echo. I don't know what.
I don't think that's for me because I have only one device on.
I had another question. I had another question. You and also Chaim Kislev have a way to compute the systolic invariant or the Eckland-Hofer invariant or the Eckland-Hofer Zender capacity for polytopes. Can you do it numerically? Can you numerically look for a maximum? Can you numerically look for a maximum?
Right. That's exactly what Julian and I did. So okay. Julian wrote a computer program to compute the systolic ratio, and then we ran some combinatorial search algorithms to find.
What's the maximum number of vertices? What's the maximum number of vertices for which you can do that?
We did a lot of computations with up to 7 vertices. With 8 vertices, it gets pretty slow.
Okay. Okay. Thanks. Thanks.
Michael, I have a question.
Michael,
I have a question. So is this formula for the only for convex torque domains? Only for convex torque domains? Or
Someone turned down their volume on their.
Yeah, this formula for the Llewellyn invariant is for monotone toric domains. I don't even know if it has to be monotone, but I do. It's definitely true, for all monotone toric domains.
For weakly convex too, or no? For weakly convex too, or no?
I haven't checked that.
Okay. Okay. Thanks. Okay.
I was supposed. I think I told you before I was going to check that, and I never got around to it. Sorry.
Okay, that's fine. Okay, that's fine.
I see in the chat somebody asked why dynamical convexity is the same as monotonicity for a toric domain. So I can answer that one. Let's see if I can add a page. No, how do I add a page? I'm a beginner at no, that's not it. I'm a beginner at this software. There's a page for me. Okay. So why is monotonicity the same as dynamical convexity? So if I have some toric domain like this, you can see where Rabe orbits. Well, the Rabe orbits are at points on the boundary. Whoops. At points on the boundary where if you take a normal vector, then this after scaling is an integer vector, and we can make the two integers relatively prime. And then for each such point on the boundary, there's actually a torus of Rabe orbits, or it's an S1 family of Rabe orbits. And those Rabe orbits fill up the entire torus, which is the moment map image of this point. And then you can say, what's the Conley-Sander index of these orbits? Well, this is a degenerate contact form, so it's a more spot contact form. But the sort of in sort of degenerate sense, the Conley-Sander index of this family of Rabe orbits is let me get this right. Well, it's basically A plus B. So after you perturb it, you end up with like A plus B plus 1 or something. I think I have to multiply by 2, I think. It's just basically 2 times A plus B. So if the domain were not monotone, then if these vectors start having negative components, then you end up with things whose Conley-Sander index is too small. That's the basic idea. The detailed calculations in our paper.
Michael, can you hear me?
Mm-hmm.
Yeah.
Yes, I hear you.
Can you hear me? Okay. Yeah. Hi. Okay. So I have a question. So at the beginning, you mentioned that for some domains, the asymptotics of the capacities from symplectic homology recovers the Lagrangian capacity. Can you say a little bit more on for which sets? Is true.
Yeah. So so this is certainly known for the ball by that was proved by Symplectic and Monka. There's a recent paper by Hind and Zhang, which gives instructions to Lagrangians in 4 dimensions, and this sort of implies the statement for some ellipsoids. And there's a more general work in progress by a student of Kai Symplectic, but I'm not sure exactly what I should say about that. So you might want to ask him.
Thanks.
So, Michael, it could be that the echo. It could be that the echo.
Okay, what can I do?
Lower your mic. Lower your mic. No, you lower the computer volume, or the computer volume, or the iPad volume.
Okay.
Is that better? Is that better?
So my iPad volume's now down to 0. So I think I can't hear anything, but I can turn on my laptop volume. So now my laptop, that's bad. The other one.
In the meanwhile, if other people have questions,
Well, maybe I have a little remark. So it concerns the question. What are the abstractions for a domain to being?
Right.
Yes, and so you see, I mean, that. Yes, and so you see, I mean, the expression is the following. So, assume that your domain, so symmetric under involution. So when it is symmetric under, transformation of order 4, and that's more or less what we. I mean, that's more or less what we. I mean, similar to what we did such a question before. In this about powers from Hamiltonian diffeomorphism, about powers from persistence model. You should look at this symmetry. Persistence model. Z2 symmetry of favorite homology. And so take homology. -1 eigenspace, -1 eigenspace, which are the multiplicity which are if you have long bars, and if you have long bars. Okay, so Claude say that nothing is understandable. Claude say that nothing is understandable. I'm sorry.
Okay, I'm gonna just catch my iPad, see if that helps. I'm just using the computer.
We still have it? Or it's okay now?
No, I could disappear, it seems.
Yeah, so now it's okay. So Michael, we don't hear you, we don't see your iPad, but
maybe that's a good thing. Maybe it was all Michael.
Yeah, I'm sorry, I don't know what was happening. We did a check yesterday. Everything.
But also
fine.
he gave a very good talk, so let's thank him also. Also, we explored how echo works, and that was also.
Michael just wanted extra clapping at the end of his talk, so he turned on the echo so that it would sound like there was twice as much clapping.
So, other questions?
I think it's still open if the smallest periodic orbit is unknotted, yeah?
Right.
That's of course also good to know in that context, that the answer to that question.
Yeah, so I was talking with Umberto about this, and it seems like the minimum action of an unknotted orbit is the normalized capacity. So if you could prove the strong Viterbo conjecture, then you would get that statement.
Yeah.
So Leonid, maybe you can raise your point again, because
okay, I'm sorry. Yeah, so now without echo, so without the Z2 symmetry. So I'm saying the following thing, that if you have a Z2 symmetry, so you not always from this Z2 symmetry, involution can take square root in Hamiltonian category. But the proof goes exactly as via barcodes of, I would say, eigenpersistence models of eigenvalue -1 for this involution, as in our paper with Yegor. How to construct examples, I don't know, but at the end, you will get an example of a domain which is invariant, let's say symmetric, but not symmetric under centrally symmetric, but not symmetric under rotation by pi/2. And of course, this domain cannot be toric. So that's the suggested approach. I didn't think about this problem, but seemingly abstraction exists in the literature and it is robust under perturbations. I think C0 for sure.
Yeah, then maybe one should also remark that one reason why toric domains should be very small in the set of all star-shaped domain is that then the dynamics on their boundaries is integrable.
But maybe you can approximate.
Yeah, maybe you can approximate. Of course, this does not exclude that there is that the interior are symplectomorphic, but evidence, but it should be very few.
Yeah, so it's a little hard to understand how the dynamics on the boundary relates just to the open domain, like the symplectomorphism class of the open domain. Does that see the boundary dynamics or not?
Sometimes it does, and sometimes it doesn't. I mean, it's not empty, but it's sometimes it sees very little, and sometimes if there are a lot of periodic orbits, it sees. Then you have relationships.
Okay.
All right. So, any other questions? Let's see. On chat, no. Okay, so no more questions. I think none. So thank you very much again, Michael.
Yeah, thanks.
Your iPad worked very well.